Okay, so welcome everybody again. So in the I-ESA conference on interoperability, it's my pleasure to welcome Professor van der Aalst that will make a keynote speech regarding process cubes, and it will be a 45-minute speech or around this time, and I hope you will enjoy it. Thank you very much.
Thanks very much. So is the mic working? To the slides? Okay, very good. So today I'm going to talk about process cubes. To do that, I need to introduce the topic of process mining, where I know that some people know a bit about, but for many of the people it will be new. I should also apologize. If you look in the proceedings, you will see a story completely unrelated to what I'm going to talk about. I would just like to say one sentence about it. Is that we started in Eindhoven a so-called data science center, the data science center of Eindhoven. I'm the scientific director of that center. It unifies 20 research groups working in this area. I think it's a very important development. So I was one of the first, perhaps the first professor in computer science in the Netherlands that actually studied computer science, because all my predecessors studied physics or mathematics. I think we are now also at the start, just as in the early 80s, that we are at the start of a new discipline, a discipline called data science. So I'm mentioning this because in the proceedings, in my job as scientific director, I think a lot about what is the profile of a data scientist, and if you look in the proceedings, you will see a discussion about that and the importance of the field. One of the ingredients in this profile of being a data scientist is process mining. So it's analyzing processes inside machines, but also processes in organizations. We would like to analyze them based on data. So before I get to the notion of process cubes, the more advanced things, I would first like to make an introduction of it. As this slide shows, process mining is linking many different things. So whereas people in the business process management area or people working on formal methods, process models, Petri nets, BPMN, BPEL, etc., they typically focus on models without actually looking at data. At the same time, there is this huge field of machine learning, data mining, evolutionary computing, and people are typically looking at a single decision rather than end-to-end processes, as the people in the business process management field are doing. So process mining is the linking pin between these two fields. We started working on that about 15 years ago. At that point in time, it was incredibly primitive. I still remember our first case studies. There people were writing on paper documents when they started to do a task and when they completed the task. Today, that's of course completely stupid. You cannot imagine that we were doing that at that point in time. But that was because I had the feeling that we cannot just make models without really looking at the relationship between data and processes, and that we cannot look at them in isolation. If you combine the two, and I will hopefully show that to you, then you can answer performance-related questions. Where are my bottlenecks? Why are my bottlenecks there? What are typical for the cases that are late? But also compliance-related questions. Where do people deviate? Why do they deviate? So we are trying to answer all of these questions. So this is another picture to position a bit what I'm talking about. So on the one end, you have the business process management field, but you could also talk about things like formal methods, people active with process models. On the other end, you have the data and machine learning field, and process mining is kind of the part connecting it. What this slide shows is that there are these two main subdisciplines of process mining, but there are many more challenges that you can look at. One is process discovery. You know nothing about the process, and you just want to discover it. And the other is conformance checking. You have a model, either discovered automatically or made by humans, and you want to check, does it fit, does it work the way that you expect it to work. So before showing you what you can do with it, I just explain you the minimal requirements, because otherwise for many of this will be very abstract, and you think, well, he has very special data, and because he has this special data, he can do these things. But by this example, I hope to convince you that that is not the case. So what we need to do process mining is information about events. So in this table, every row corresponds to an event. And in this case, every event is a student making an exam and getting a particular grade for it. So what are the minimal requirements for process mining? Every event should refer to a process instance, a case ID. In this case, a case ID is the student studying a particular program. You should have an activity name, the building blocks that you would see in the process model as activities. And we need to have a timestamp. That's all we need. Of course, if we have more information, like in this case the grades, we can use that information to, for example, and that is very relevant for the notion of process cubes that I will explain, that, for example, you would like to know the difference between the students that studied and passed the course and the students that studied and failed the course. And for that, you are using this other data. Another example, this is a typical event log from order processing. Every line corresponds to an activity executed in the context of processing an order. So again, the first column is the order number, that's the case ID. The second column is the activity name. The third column is a timestamp. This is what we need in order to do process mining. But if you have additional information like which person executed it, what product it was, the quantity, we can also use that type of information. The last example, in a hospital, we have been applying this in more than 10 hospitals. Any hospital has approximately 800 tables with patient data. And each of these 800 tables will contain a reference to the patient. Yeah, so that's something that we have. That's in the first column. And then we can derive what kind of activity has been executed. We know what are the timestamps. This is, again, the minimal requirement. But it may be that you know something about the resource, that you know the age of the patient, and all kinds of other data. Yeah? So this is the minimal requirement that we need. And I hope that everybody can imagine any organization is loaded with this type of data. Any device of the future, the Internet of Things, is recording this type of data. So this type of data is everywhere. And unlike classical data mining data, there is this strong assumption that we know events and we know when they happened. But you can imagine it's there at many places. So we use this type of data to discover desire lines. So you can think of this as process discovery. If you look at a girl with a red coat, that girl is showing what people are doing, whereas the official path is something completely different. So using process discovery, we don't want to know where the official path is, we want to know what people actually do. So the same as if you would look at student data, we are not interested in what the official curriculum is. We have designed that, but you would like to see what students actually study. And that is often very different, as you can see in this picture. This is the quality is not very good, but you can see it's very funny. Here you see that people have built a very safe system to protect people from going in, but the desire lines show you something completely different. And this is a typical phenomenon that you see if you do process mining, and you have the ability to really look at the raw data rather than any aggregate data. So this is the basic idea, and I will show you a demo of some tools, how this works in action. But first I would like to ask a quiz question. This is an example of a process model. The notation is a Petri net. So the squares are transitions, the circles are places, and for example, E is only possible if there is a token in P1 and a token in P2. if there is a token in P1 and P2, it can execute and put a token in P3 and P4. So I could have used any other notation, but this is the notation that we often use internally and then represent it in any language that a person would like to see. And this simple process model is able to generate the traces that you see at the bottom. So we always start with A, we always end in D, and in the middle we can do a B and a C in any order, or we just do an E. If you look at these traces and you look at this process model, my first question to you is, suppose now that we would like to have a model with less behavior, because process mining is about relating behavior that you see to models. So who can answer to me, if I would like to remove behavior, what can I do in general terms? Nobody? You can remove a transition, good. And what more can you do? You can remove places. So adding transitions, adding activities is adding behavior, and removing places is removing constraints, is allowing for more behavior. So many of the process discovery techniques are using this kind of mechanism to reduce behavior if you don't see behavior. So it's really simple. So if I would remove E and I would add a place between B and C, the only trace that would still be possible is A, B, C, D. This, of course, is a tiny example, but it gives you an idea. So if you could answer the previous question, I hope that you can also answer this question. So how can we add behavior? We can add behavior by adding transitions or removing places. And it's important that you understand also the removing of places. So if we would remove P1, then we can do B already before A, because B no longer has to wait until A finishes it. So removing P1 is allowing for more behavior, and adding F as an alternative to C is also adding behavior. So now we get the red traces that are also possible. So that's the basic idea of how you can approach process mining. Adding transitions, adding places, removing places. And there is a whole range of analysis techniques to automatically construct models. So here you can see, let's say, some of the algorithms that are available today. I will not explain them in any detail. I just would like to point out this technique. And if you look at this technique, it just looks at the question, can I add a place with particular connections or not? So in this case, the question is, can I add C? And C has certain input transitions, certain output transitions, and certain transitions that take something and put it back. And you can rewrite this question into a system of inequations for every trace and every prefix of a trace that you see. And the phenomenon that should happen is that the place at the end is empty, and in between it never gets negative. So I can rewrite a huge system of inequations, and solutions of this system of inequations are places. Just to give you a bit of the flavor of the types of analysis techniques that are behind it, that it is not just magic. So by doing that, one of the interesting things is that we can connect data and processes. We can connect business people and IT people. They typically have difficulties talking to each other, especially if you start talking with them about a BPMN model or a BPEL specification or something like that. They will not be able to talk to each other. But if you do process mining, it is based on the real data, then suddenly these two groups of people can find each other. And I think for this audience, that's a very relevant thing. It's the link between BPM and business intelligence. It's the link between performance and compliance. You can do it at design time, but you can also do it at runtime. At runtime, you can discover that something is behaving differently than it did before. Or at runtime, you can discover that probably tomorrow there will be a problem in your process. Just learning over historic information and combining that with current data. So what is important, because the only way that I can explain it to you, let's say in very basic terms, is that I talk about A, B, C, and D. But you have to realize that event data is much richer than just control flow. So we have information about time, we have information about data. So it's like here, it's not just a wall, it's not just control flow, but it has all these other aspects in it. You build models that are not just control flow models, but that show you bottlenecks, that show you deviations, that show you frequencies, that can show you where the costs emerge, all of these things, where there are risks that something goes wrong. So this is the whole, it's an overview of the whole process mining spectrum. What I will talk about today is mostly discovery and perhaps a bit of performance analysis and compliance checking, but you have to realize that there is much more. And that it's also used in a predictive sense, at runtime to predict things, that it's also about, not just about control flow, but about many more aspects. So I could show you more and more slides, but perhaps the best thing to do it is to show you something, and I'm going to show you very briefly something from two tools. The first tool looks like this. It's like a very powerful tool. Actually, it supports 600 different types of analysis. And the things that I will show you are, let's say, one or two of these, the 600 plugins that can do all of these types of analysis. It's extremely powerful. So this is like the de facto standard in the scientific world to do, let's say, these types of algorithms. But it's incredibly complicated to use by people in industry because they get confused by this knife, and you can understand why. That's why I'm very happy that in recent years there are also many commercial tools kind of using RRDs, making it very simple. So here there are a bunch of tool names of tools that provide, let's say, this type of analysis. I will show you something from Disco, which you can see in the top corner. This is a company that was started by two of my PhDs, and it's kind of one of the leading companies in this area. Okay, let me just show you something. So first I will show you this very complicated knife. So now it's loading all the plugins. Yeah, so now it started. So now I started ProM, and what I now need to load is I need to load raw data. And I will show you some of the characteristics of the data first, but I'm now just going to load a log file and just show a bit what you can do with it. So I'm loading a log file from a company called Vestia. It's a housing agency. And if we look at the data, you can see that this is information about 200 apartments changing from one tenant to another tenant. So somebody is renting an apartment and then says, okay, I want to stop renting it. We have 208 cases and we have 6,000 events. I can show you some of these things. So these are Dutch terms, but this is, for example, one house where there were 31 events in which the house switched from one tenant to another tenant. So the first one is register the cancellation of the rent. The second one is register the future address of the tenant. The third activity means that plan the first inspection of the house. And then there are things related to payments, people need to repair things, etc., etc. It's these type of activities. I can also view this data in another way. And then let me sort them by start time. So now every line that you see, every horizontal line that you see in this diagram corresponds to a house. So there's one house. And for this one house, there are many events, and the events are dots. And the position of the dot on the x-axis corresponds to the time at which something happened. Yeah? So if you now take a look at this, does somebody see something strange? So we are looking at raw data, just events. So who can see something strange? Sorry? Yeah, that's very good. So you see certain lines in this diagram. For example, here you see very clearly one. And I can zoom into it. And then, so for example, I can just look at this part. And now you see that there are many events happening at the same time, the same type of event, and that's very suspicious. That means that this case has been waiting for weeks. And then somebody came in the office and just flushed everything, and then it was gone. Another thing that you can see is that the line is curved. That means that the inflow is increasing. I can view this in event data in a different way. I can also take relative time and then sort by duration. And then you can see that the duration of these cases, so now the top ones are the shortest one. Everything starts at time 0. So you can see that there is a very, there are some cases that are very short, and there are cases that are very long. And again, we did not do any process mining yet. I'm just showing you how you can interact with this event data and what kind of data you can get from this. Then given something like this, I can mine a process model from it. In this case, I'm using the fuzzy miner. So what you now see, if you have very good eyes, you see the process model showing all the activities. So you can zoom in if you want. And so here you see the type of activities that I was talking about before. The thickness of the line is saying something about the frequency, etc., etc. I can, as such a picture, people find that often very intimidating when they see something like this, but you can make it as simple as you want. So if I move this up, you can see that certain activities disappear or are pushed down to a lower level. So for example, if we look now, then we see that we have a simpler process model. Just like Google Maps, I'm zooming in and I'm zooming out. Then people, when they look at these diagrams, they often don't believe you. Because I just loaded the raw data, I showed this diagram, and they say, well, but this is not the way that we do it. What we do then is we typically do this. What I'm now doing is I've learned a model, a process model, and I'm going to connect it with a log. So I have a model, I have an event log, and now I'm going to replay the event log on top of that model. And then you get something like this. So what you see now, and this is so this is a process that has no meaning to you. So this looks perhaps strange. But every of these moving tokens that you see is referring to a real house. So if people now say, well, it is not true or something like that, and you can say, okay, let's look up this particular apartment and let's see what happens with it. So if people are denying that there is a bottleneck at a certain point in time, you can show that that is not the case. So a mining technique like this is very, it's very easy to use, but the models are typically not executable. They are just descriptive. We can also generate executable models, but for that I take a simpler event log. So now I've loaded another event log. Now I can apply the alpha algorithm. I get a process model like this, and now you can see it's a Petri net, as I was showing in the beginning, and it's using the type of techniques that I was explaining to you before, deciding whether a place can be added or not. Also, with these types of things, you can simplify things. Then I need to link it to a log again. Let me go back. I selected the wrong log. Sorry about this. But you can see how fast it goes. So all these things have in common that I'm applying a plugin on top of a model. So what you now see is that I see a PetriNet, and I have a very precise executable model, but I can also play with the level of granularity that I have. But at any point in time, I have a model that I can save as a BPEL file that I can subsequently execute, or as a BPMN model or whatever. So it's more precise than the other models that I was showing. One of the reasons why I was also showing this event log is that it also contains information about people. So here in this log, I can see which person executes what activity. So I can automatically create a social network. And for the people that have a background in social network analysis, they know that you can rank the importance of a person based, for example, how many paths have to go through that person to go from one person to another person. And so which people are the spiders in the hub, and I can take, for example, betweenness and then decide on the size by ranking. I can also show a view like this, but that doesn't work well on this beamer here. So I can just look at which people are doing activities and how is work handed over from one person to another person, taking into account the process model to see whether there was really a causality that work was handed over from one person to another person. So this shows that we can use time, we can use resource and all kinds of other things. So this was the tool with the 600 plugins, and I've showed you 3. I'm not going to show the other 500 something. Instead, I'm going to show you a commercial tool. We don't have internet here. I have. So now I'm going to load a simple CSV file. And here you can clearly see all the information that we have. So here you see the first column is referring to a house. The second column is a code and an activity name. Here in this column, in this log, we are hiding who executed particular things, and we have a timestamp. So this is how simple the data is. It's just a CSV file. And if I load this CSV file, then I can import it, and poof, I have my model. And I again can play with it. I can show you, this is the way that it really works. If we show all the activities, and if we show some more paths, then you will see that it gets more and more complicated. So this is what reality is like. It's like the same as if you would show a map of France, and you would show every road. It's incredibly complicated. So you need to have this seamless abstraction that you can make things as simple as you want. And so now I show all the activities, but I just show the highways through the process model. And if I reduce this, then I'm showing the highways, but I'm only showing the bigger cities, not the smaller ones. That's the metaphor that you should use here. So the things that light up in blue are the things that are frequent. So for example, you can take a look from the beginning. So here is, you always start by registering that you want to cancel your rent. What we could see in the example, often people record their future address, etc., etc. So this is frequency. I can also show a view based on performance. And now you can see, for example, that on average, let me point it here, on average it takes 3.1 days after the registration before you know the future address. It takes 7.2 days before canceling the rent and making the appointment for the first inspection. So highlighted in red are the things that take most time, but here it's a bit unbalanced. So you see that typically there are 65 days between these two activities. There are 34 weeks between these two. So you can immediately see the bottlenecks. And one of the things that I really would like you to remember is that I loaded a CSV file, nothing more, with just events, and I get a model that is showing me where are the bottlenecks, how frequent are things, etc., etc. And I hope that you see how widely applicable this is, and how surprising is, if you didn't hear about this, that you did not hear about this before. And that's, and why not more people are working on these types of things. Okay, so we have seen a complicated tool, we have seen a simple tool. And this is standard practice. We can use this type of technology, it works. But this is a very young field with an enormous amount of open research questions that you can answer. And one of the things that I would like to highlight here is a bit the problem of dealing with big data and dealing with the situation that you're often not interested in the analysis of one homogeneous group of cases, but that you're typically interested in analyzing different groups of cases and comparing them, or different organizations. And that is the basic idea behind process cubes. So let me start by introducing it very simple. It's the idea of OLAP, but then for processes. So normally, if you have a set of numbers, then you can compute an average. If you use a spreadsheet, if you use an OLAP tool, you compute sums, averages, and these types of things. If you have a bunch of event data, rather than compute, then your model is not an average, your model is not a sum, but your model is a process model, or a social network, or something like that. So you want to create a model, and you're not interested in a single model or a single number, you're typically interested in multiple numbers. And so here you see it's like meant a bit as a joke for the people in Eindhoven. But here I distinguish between the students that failed and the students that passed. The students that studied in Eindhoven at the Higher School of Economics in Moscow, where I have a second appointment, and at QUT in Brisbane, where I have a third appointment. And I compare the number of hours studied by students and how many students fail or don't fail at a particular location. So if you look at the spreadsheet, if you look at an OLAP tool, this is typically the things that you do. And it's extremely useful. But now I want to lift this to the level of processes. So I take the same thing, and I now would like to compare processes between these different universities, between these different groups of students. And this is what I call comparative process mining. Not mining for a single process, but comparing different processes. And again, the applications are very broad, and it's a difficult question. So as a child, you probably did this. So you have these pictures, and you need to find the differences. And there's an illustration that you need tool support for this, and we are just starting to think about this. We are really at the beginning of, let's say, dealing with this problem that we can easily compare two processes, where are differences in bottlenecks, where are differences in compliance, and these types of things. Let me show you some examples illustrating how relevant this is. I'm sure that many of you have rented a car. I've been renting cars all over the world, and I typically rent my car with Hertz. And for me, it is very surprising if I rent a car in Italy or I rent a car in Australia, the procedures are different. It's the same company, but the procedures are different. So also there are different groups of customers that are treated in a different way. And maybe Hertz is dealing with things differently in the holiday peak period than in other periods. So that is how we get a cube of events. And we are interested in knowing the processes in each of these cells. Another project, so the first was like a motivating example. This is a project that has been running for 4 years, where our goal is to compare 10 Dutch municipalities from whom we have all the process models and from whom we have all the event data that they have. And it is very surprising, these Dutch municipalities, by law, they all should do the same, but in practice, they all do it differently. And so, for example, in one municipality, you need to pay at the beginning. In another municipality, you pay at the end. That is one variation, but there are many of these variations. And these 10 Dutch municipalities where we are working with, they are very interested in learning from each other. Why is one municipality doing something with less people faster than another municipality? So although they are using, they are also sharing, they have a shared IT center, so they're also sharing some infrastructure, and they are interested in understanding why they are working in a different way. And again, we can build a cube. So for example, one thing that is very clear if we do this type of analysis is that the processes are not always the same. If the government changes the law, you can see that in the event logs. So it directly has an effect. I spent some time in Australia, and if you go to Australia, at least when I go to Australia, there are two options. When I come, the country is flooded. I've been in Brisbane twice while the city got flooded, or the country is on fire. So the university there, QUT, is working a lot with Suncorp, and these people in Suncorp, they will explain very clear to you, there is no such thing as the process. It changes constantly because of the workload and other types of things. So one cannot think in terms of a single model, that's the way that things are being executed. At the time that Brisbane was flooded and you get hundreds of thousands of insurance claims at once, you cannot do business as you usually did. So that's a very interesting case to see how organizations are behaving with respect to these changes. And again, you see a cube. So what I'm showing here, so that was the time period. On the other dimension, you can see that Suncorp is one company, but they have at least a dozen different brands. Certain brands aiming at young people, people that want to take more risks, etc., etc. So they have different brands that you can see at the bottom. And they also offer different types of insurances. Home insurance, car insurance, personal insurance, etc. And for each of these cells, you can again build these process models and try to understand the differences. This is me teaching. And we are interested in understanding why certain students are more successful than other students, why certain courses become a massacre while other courses do not become a massacre. Typically, my courses are a massacre, by the way, but that's between us. So again, you can build a cube. So in the Dutch system, we have marks from 1 to 10. Above a 6 is you pass. So we can populate such a cube. So here you see the example that you distinguish between students that, for example, are male and female. And we have lots of international students. In our master program, more than half of the students are foreign students. And we can distinguish students based on their nationality. Then for every cell, we can start building models, the kind of models that I showed you before. And so this is a very interesting case study to do these types of things. So here you see the dotted chart that I showed you earlier in ProM. And again, you see these lines. And these lines, these red lines that you see here, they correspond to students taking an exam. And of course, they should take the exam on the same day. And that's right. So all the red dots are exam attempts. All the dots of another color are students watching my video lectures. And every different, the color of the dot corresponds to a student watching a particular lecture that was taped. And so what you can see is that many students just start, they watch at the beginning, they watch just for the exam, so you can see all of this kind of phenomena. I'm now going to zoom into a particular generation to see, let's say, what their study behavior is. So here I show you, and the data sets that I have here are very small. As I said, we are just starting to work on this topic. So here I distinguish between students that passed or did not pass in one dimension. In the other dimension, Dutch students versus international students. And I can just look at the dots, and here you see all the events that I've been considering. This doesn't help you very much, but it just shows you that you can have these cube-like forms. And to show multiple process models here is a bit confusing. This is perhaps more clear to you. The process model that you see on the one side is the process followed by the students that passed. The process model on the other side is the process followed by the student that failed. So now I have a very simple cube with just two cells, just to make the point. So there is something like the ideal curriculum. The ideal curriculum is that students watch lecture 1, lecture 2, lecture 3, lecture 4, etc., and then makes the exam, and then is done. That's the ideal scenario. And we have a notion of conformance. I don't talk about the topic of conformance checking, but given a model, we can measure how well it fits reality. The fitness of the students that follow this ideal scenario is very low. It's 0.37. So that's a low number, but yeah, that's the way that people study. What is very reassuring for me is that the students that fail, they have a conformance which is significantly lower. It's just 0.28. So if you look at this process model, so here is where the students that fail start. Let me start here. Here is where the students that pass start. And what they typically do is they start by watching the first lecture. That's their first starting point. And then sequentially go through the lectures. If I look at the students that fail, I hope you can guess what is their first event typically. That's making the exam without having seen a single lecture. But this is like showing that these types of things work. So these are very obvious, but if you have larger data sets, you can do much more sophisticated things. How am I doing in time? Okay, so that was the element of process cubes dealing with multidimensional data and immediately going to these processes. Now I would like to bring the big data question a bit into this thing. What you could see from the tools that I just showed you, process mining is much faster than any of the data mining tools available today. Typically our algorithms are linear in the size of the log, exponential in the number of activities. They're quite good to get the first overview. To really do a detailed analysis, that is much more time consuming. And also the types of logs that we are sometimes confronted with, they are so incredible that many people talk about big data, about large amounts of data, but if you have algorithms that are exponential, then if a student comes with a hard disk of 2 terabytes of compressed data from, I don't know, one of the biggest search engines in China, then you cannot analyze that. So there is the challenge to be able to deal with bigger data sets. So for the people that enjoy Star Trek, this is data, and this is big data. So we want to be able to deal with big data. And the obvious way to deal with big data is to kind of make this big problem into many smaller problems. And so we can do this very well at a level of, let's say, up to a couple of hundred of activities, up to a couple of thousands of events. That's no problem. But what if you have more than 1 million cases? What if you have more than 100 million events? What if you have more than 1,000 activities? And especially the last one is very nasty because it's typically exponential in the number of different activities. So then you need to do something smart. So what we do is we distinguish two types of ways of improving this. And we split the log and we talk about so-called horizontal and vertical decomposition. We want to make this big log into a smaller log, then apply our process mining tools to all these smaller logs, and then combine the result in an overall log. So let me just sketch the idea. This is trivial. You don't have to think about it. If you have a log consisting of many cases, then you can just make two buckets, half of the cases in one bucket, half of the cases in another bucket, apply your process mining techniques to that, and then find a way of merging it. In terms of conformance checking, this is really trivial to do. For the other algorithm, you need to do a bit more. But because the algorithms are linear in the size of the log, you don't gain that much. You can use more computer power concurrently, but there's not that much you can gain. If you kind of put them into buckets that are homogeneous, of course you can do more. But I'm very much interested in cutting the log in a different way. So what you now see here is that I have this event log and I put certain sets of activities in one bucket and I put certain sets of activities in another bucket. That's the idea. To make it visually, suppose that I take the log that I had in the beginning and I have one bucket where I have the activities A, B, E, F, G. And I have another bucket where I just have the activities B, C, D, E. And so if we look at one case, there is part of the cases on one side, part of the cases on the other side. And then if I learn process models for each of these two buckets, and then put them on top of each other, I get the model that I would like to have. That's the basic idea of trying to deal with this exponential factor in the size of the log. So what is really important to see is that you can split a log in various things. So if you look the part below, that is trivial. So if you take this event log that you see here, so the event log in the middle, and you construct a model, you immediately get that model. You can have this partitioning, where you put the traces into particular buckets, learn the models, and then you need to merge the models into the model in the middle. But I'm interested in what you see at the top. I put certain activities in one bucket, other activities in another bucket. And then I apply process mining to it. And I want to have a speed up which is much better than just by doing it in parallel. I hope that you can see the relationship to process cubes. There you're also partitioning your event data. So you can have lots of smaller cells, quickly compute something, and then merge the results into bigger things. That's the relationship. So the idea of decomposed conformance checking. So conformance checking is you have an event log and you have a model, and you want to see how well these two fit to one another. That problem is sketched here, how you can approach it to distribute it. So you take one model and you cut the model into smaller parts. You take the log and you cut the log into smaller parts. Then you check the compliance. So how well the reality conforms to this small model, reality conforms to this small model, etc., and then you merge the results. So that, I hope that you can see the idea. That's one of the things that we're trying to do. Let me give you an example. And again, it's very funny because I have to show this with examples. And so this is intended for process models having thousands of activities. But I cannot fit that onto a slide. So I need to have these small ABCD examples. So if you look at the model in the top, I can break that down into the smaller parts that you see here, just by projecting on the activities. And we have different strategies for doing this. So if you have such a decomposition, and there are really very weak requirements on such a decomposition, and there are many ways that you can do it, then checking whether the event log corresponds to the big model can be translated into lots of smaller checks of smaller process, smaller event logs compared to a small model fragment. And just to give a bit of the flavor, without expecting that you understand the details of it, I just show you that I'm now replaying the trace that you see there on top of all these smaller models and on top of the bigger model. So in the first, so we have cut up the event log, we have cut up the process models. In the overall model, we want to do an A. That means that we need to do an A in all the process model fragments where an A appears. So then we execute it. So we execute it in the overall model and in all the different fragments. So I can repeat that. Now I need to do a B. B appears only in one model. So I only need to execute it at one place. Now I need to do a C. C is appearing in two models. I execute it again. So now you may think, okay, you're doing that, but what do you gain by that? So how precise is that? Well, remember, all of these algorithms are exponential in the number of different activities. So it's much faster to check all of these smaller problems, even if you do one after the other, than checking the overall problem. And another nice result is this result that I'm very proud of, is the result that if there is no problem in the bigger model, I will not find any problem in the smaller models. If there is a problem in the big model, I will find the model in one of these smaller models. So something fits perfectly everywhere in the big model and all the smaller models. And if it doesn't fit somewhere, I will see it on both sides. And this is something, it is a very general result, so it holds for any type of process model for which I do this very weak notion of a valid decomposition. And there are many ways to do it. If you're interested in this result, you can see the reference there. So this is a nice theoretical result. What does it mean in practice? In practice, it means this. So here you see a sketch of the IDs of the process models that we are looking at, much bigger than the other one. The one that you see there is the process model that is shown here. And unfortunately, the bottom of the slide is missing. So all the black bar charts, they refer to the situation where you just check the overall problem. The other bar charts are where we are doing it in a smart, decomposed way. And you can see first, so our first result was this gray boundary. And the result that we now have is, let's say, the red one that you see. That's the best technique that we have at this point in time. So you have to imagine that for the model that you see on top, after 10 hours of computation time, we just stopped the computer. And now we can do it in, I don't know, a few seconds. That shows that this decomposition is really working. Okay, so that was conformance checking. You have to believe me, we can also do this for discovery. It's exactly the same idea. So this is to show that dealing with large amounts of data is creating all kinds of interesting challenges where you can do beautiful research on. Okay, to come to a conclusion, I talked to you about audit trails. I hope that you see that they are everywhere, also that processes are everywhere. And in such a situation, you can apply process mining. If you want to do this, then there are, so I'm now sketching you a smooth story. But if you do the reality of process mining, you will see that there are many things that you can still work on. It's really an area with an infinite supply of research problems. If I would have 50 PhD problems, it would be a problem for my time, but not the ideas that I have of the open problems that you can still attack here. So if you look at the challenges, once we understand well how we can mine a single process, it becomes interesting to see how we can compare processes. And I hope that I showed you the relevance of that. is a new area. Hardly any work has been done there. Then everybody is talking about big data. And you can see that process mining algorithms are typically efficient, but you can gain a lot of speed by analyzing them in a smart way. If you got interested in the topic and want to learn more, then you can go to this website, or you can read the process mining book. I would like to stop here, and thank you for your attention, and hope that there are a few questions. Thank you.
Why have you been using... Thank you. Did you understand me?
Yeah.
Okay. Why not?
So far, you only said kind things.
Yes. Now the question comes.
Good.
I would be interested, why not use another underlying algorithm, for example, the abstract state machines, where you have more parallelism built in the mathematical mechanisms, where you have, for example, the notion of an agent, which would allow us to map towards roles in processes, which might also be of an advantage, and this is what learning from your slides about these parallel problems might be of advantage when you distribute the models to smaller parts. You could use also the ESM notion there.
So your question relates a bit to the representational bias. So so in data mining, or in mining in general, you need to think, what is the representation that you're using as a search space? And in that sense, my talk has been perhaps a bit misleading, because I've showed you Petri nets as a very basic thing to do. If you look at our algorithms, we are typically using a wide range of representations. So we have tree-like models, which are more, you could compare them a bit to the typical process algebraic operators, but then in a tree shape, where we break down the problem into smaller problems. We also have something like, which we call C-nets. It's a representation tailored towards process mining. There are many people that have advised me the idea to use the type of kind of representations that you have. And I think it's a very good question. And I would also like to make a provocative statement, an extremely provocative statement. Models are crap, representations are crap if you cannot discover them. So I work in the area of Petri nets. In the area of Petri nets, many people are fond of Petri nets where the token is again a net. I love it. I worked on it myself. There are all kinds of exotic formalisms that you can think of. And I view it more like physics. If we cannot discover it, it's not natural. And with the type of representation that you're talking about, I'm convinced that you can benefit from such representations. But what you need to do is you need to enrich the log with some more information, like the actor or the type of things. And if you take logs that you enrich with a bit more of that information, I'm sure you can exploit it during the mining phase. But unfortunately, it's a wide open area, so perhaps a good idea for a PhD project to work on that topic. But do you agree with me if I say, like in physics, representations only make sense if you can discover them?
Well, yes and no. It's like in physics, there have been theories around, and before they were able to prove it. On the other hand side, people have observed element data, basically, and derived theories. So a model basically is a theory, and the theory is some kind of looking glass, which allows you to see some more details, the same thing that you do. Is it better? I don't know, but over time the theories change and the model's getting richer, and And this time, yeah, all models are crap, because tomorrow we have new models, we have enriched models, we have more details, and this type of move on, and then do also bring it back to reality, the model, funnel the model and the theories back to reality. This is something what we should, as researchers, do in order to give back to the society part of what we do.
So I think we agree, but it's an encouragement to look at what kind of higher level models you could think of, and then thinking of where in reality could you observe the kind of information that you need to derive these higher level models.
Yeah, but also try different theories, try different looking glasses, and try to understand better or take a different angle to move on the science itself.
But like I was saying, that in ProM there are these 600 plugins, but you should know that many of them are working on different representations than just battery nets. You'll see a wide variety of things there.
Thank you.
Thank you for your presentation. So you talked about traces and logs. So I want to ask if you, if traces that you use are already modeled.
Sorry,
modeled already modeled traces, or you use data in bulky.
So all the things that I showed you were based on real data. So data of things that. So when I was giving the demo, I was using no model. The model was derived on the fly. So there was no modeling inside. It was created automatically. However, we also have techniques where if you have an existing model, like a belief of how things should be, or like a happy path type of process model, then we can analyze where reality deviates. And we can even create models that are like a compromise between what you have modeled and what happens in reality. Like you can seamlessly play between these two.
Thank you.
Is that an answer to your question?
Yeah. I have another question. Is if there is some semantic aspects that you use to do the process mining about activities, if you have some. If you use some semantic aspects when you do this process mining about activities.
So it's of course incredibly important that you have so that somewhere there is an ontology, whether it's explicit or not explicit. That's very important. I can tell you a very nice anecdote. We have been working with Philips Healthcare for the last 7 years. So their X-ray machines are producing enormous amounts of event data that are collected by Philips to understand how are the machines used in the field, when do they break down, why do they break down, can we predict that they are going to break down. So a very rich source of data. But the engineers that are programming this, they just have write statements in the code that says, now I write this to the event log. And there when we started, we had the funny experience that, for example, depending on the language setting of the machine, whether it was set to French or whether it was set to German, the logs would be different. So there was an engineer that thought that he was very helpful in kind of customizing the log, but he was killing the semantical aspect. So I think in the background, semantics are very important. We typically, in our event logs, assume that that has been resolved. And if you, I don't know, look at SAP data, it is also like that. Because there is something like an ontology, although it is not very explicit.
Okay. Thank you.
Yeah.
In fact, PetriNet was invoked, but what variant of PetriNets? Because in your description of processes, in fact, the control flow is well described, but we know we have communication flow, and there is another problem when the activities are fully automated, or the activity are human, or whether they use or not a huge volume of data.
Yeah. So as I said, my talk is a bit misleading because I'm showing the simple control flow models. But for example, I was talking about conformance checking. And conformance checking can be done with respect to a Petri net that has data in it, so rules, that has temporal aspects in it, and that has resource aspects in it. And then we can also do that. We also worked on discovery techniques, where we discover not just the control flow, but also the organizational model, decision trees for all the decisions, etc., etc. So we can generate richer models than just a control flow.
Thank you for your presentation. You discussed the conformance checking and also the discovery, but what about the recommendation? For example, for your students, since it is a 1 year of study, is a long-term project, a long-term process, what do you recommend to them on the fly?
So we did quite a bit of research on that. I had 2 PhDs focusing on that topic, and I think 5 people doing a master thesis on taking historic information and then saying something about the cases that are now in the system, and like predicting the remaining flow time. And if you can do a prediction, you can also recommend what are the best actions. So there are techniques available. I would not say that they are very good, but there are 2 very important practical problems. The first one is conceptual. The conceptual problem is that processes often change while you are observing them. So if you do recommendations, you have to be very careful that you're not recommending something that was a best practice a year ago. And so you need to look at concept drift, whether your process is changing when you recommend certain things. The other thing is that I've been working on workflow technology for, I don't know, 25 years. I very rarely succeeded in selling a university workflow management system to a company, because if it is used in an operational setting, they want to use commercial software. If I come with ProM or any other types of analysis tool, it's very easy. They can do it, because if the analysis tool doesn't work, nothing happens. If you go to recommendations, there is the requirement that you build it into the real information system really used in the work practice. And that is difficult. So I think this is also something where industry plays an incredibly important role to make sure that these recommendations can also be implemented. But I'm sure it will happen.
Okay, can we ask a question from this side, from Paris? Can you hear me? Do you hear us from this side?
I cannot hear you, sorry.
Paris talking.
If there's somebody that can... No, I know, but if there's somebody that heard the question, then he perhaps...
Thank you very much for your talk, and we've got a question here from David Chevalarias.
Yes. Hello. So I have just a question about, do you hear me? Can you hear me?
Now I can hear you, yeah. And myself.
So when you have very, very large data sets, data about blocks, do things in real time or even after, but it's large, do you have a possibility do you have thought about how you can distribute the processing of the data? Or are you software which is compatible with the notion of distributing the processing of the logs? In a way or not?
So the thing that we focused on is distributing process mining algorithms. If you have a distributed architecture, perhaps it should sound like I'm on the moon. Yeah. So if you have a distributed architecture, like a Hadoop or MapReduce type of environment, there are many of the ingredients of a process mining algorithm that you can let be handled by such a platform. So we did not do that ourselves, but it is clear that it can be done, and I think it's not very difficult. But our focus has been primarily on going to the process mining algorithm itself. But I think that's an orthogonal question to using Hadoop and all of these types of things, and I think that's very much possible. If you look at our software, it's a pluggable platform which you can distribute. So for example, we did distributed genetic process mining algorithms where we are distributing this over a grid. So the software has been built in such a way that that can be done. Does that answer your question?
Yeah, yes, thank you.
Thank you.
Okay, thank you very much. I think that we are just running here out of time, so we personally have other questions, but I have to keep myself silent about these questions. We just would like to thank you very much, and then we will proceed with other presentations here locally in Paris. And actually, it's a presentation from someone from Albi. So have a nice, good conference, fruitful exchanges, and maybe we will meet sometime here in Paris or in Albi or somewhere else. Okay, thank you.
Thank you.
Au revoir Albi, puis à bientôt.
Thank you.